Okay, we're going to talk about forces, motion, distance, time, velocity graphs, and stopping distance. One of the most common questions that we get in the GCSEs is about scalars and vectors. You have to be able to identify whether or not a quantity or a number is a scalar number or a vector number. So scalars are things that we measure that have a magnitude, and that just means a size, so something like 3, and it will also include a unit, so meters, only. Vectors are things that we measure that have both magnitude, so something with a number and a unit, and a direction, so 3 meters left. That would be a vector. Sometimes direction is important. In a crash, the direction as well as the speed of the vehicles will determine how much damage is caused. So if I have vehicle A going towards vehicle B, and vehicle B is going in the opposite direction, then that is going to be a much bigger deal than if both vehicles are going in the same direction. So sometimes direction is important. Examples of scalars, direction. So if I started at A here, and then I went all the way around and I went to B, that would be called direction, because the direction of the movement has changed so many times. There's no one direction that I have been walking in. So we just give that as a general term, direction. Displacement is a straight line distance between 2 points. Speed, measured in meters per second, will have very many different directions as well, up, down, left, right, north, west, whereas velocity will be speed in a given direction. Mass measured in kilograms, it's a measure of the amount of stuff in a thing, or how difficult it is to move it with a force. So bigger mass means it's more difficult to move. This is called inertial mass. And every force is going to have, including weight, is going to have a direction. So gravity is 10 newtons per kilogram. Gravitational field strength, pardon me, is 10 newtons per kilogram. And if I have something that weighs 1 kilogram, then it will have a force of 10 newtons downwards. Temperature measured in degrees Celsius. Yes, the numbers can go up and down. So 3 is going to go up to 4, and then it's going to go down to 2, but it doesn't have a direction. You can't have 2 degrees Celsius left. Energy measured in joules is the ability to do work or the amount of energy transferred. It doesn't have a direction. It's just a description of how much work can happen. Acceleration is the change in velocity, delta v, divided by t. And because it's a change in velocity, it means acceleration is also a vector. And momentum, momentum is equal to mass times velocity, is a measure of how much something is moving. And here are those definitions up on the screen. You can pause it now and have a read if you wish. And here's some questions. Again, 10 seconds each slide. And the answers. Definitions of speed and velocity. And a calculation, an example of what it looks like. Another one. And another one. The average speed is the speed of an object over an entire journey. So if I started off at A and then I moved along to B and I was going 2 meters per second there, and then I went to C and I was going 10 meters per second, and then I went to D and I was going 1 meter per second. The average speed would be the total distance from A to D divided by the total time taken. The instantaneous speed is the speed of an object at a given moment in time. So the instantaneous speed here would be 2 meters per second. Here would be 1 meter per second. The speedometer in a car gives the instantaneous speed of the car. Now, distance time graphs can be used to represent the motions of objects, and the different gradients or steepnesses of the line in the graph show different motions of the object. The shapes of line that you need to know are shown opposite. So we can have a line that's going up really steeply, a line that's not going up as steeply, a line that's got no gradient, and a line that is going back downwards. On the y-axis, we will have distance, usually in meters, and on the x-axis, we will have time in seconds. What does this mean? Well, object started moving at time equals 0, and then after 1, 2, 3 seconds, it had gone a distance of 1, 2.5 meters. So this object traveled 2.5 meters in 3 seconds, and then that will give me the amount of speed of the average speed of the object. In the same amount of time, this green line has managed to go 1, 2, 3, 4, 5, 6, 7 units of distance. Now, because it went a greater distance in the same amount of time, because the green line went a greater distance in the same amount of time as the red line, then we know that this has got a faster, greater average velocity, average speed. Now, between the time of 3 seconds, and that's 3, 4, 5, 6, 7 seconds, this object did not increase its distance at all. So it was a stationary object. It wasn't moving. And if the distance is decreasing, it means it's going back to the start. So what we see here is that something has driven or walked or something, stayed still for a certain amount of time, and then walked back to where it started, or driven, or whatever you wish. Here's some questions. And remember, you find the distance, time, and the answers. Acceleration is the change in velocity divided by the amount of time taken. When objects accelerate, they can be changing speed or changing direction. Because this is a change in velocity, and velocity is a vector, if I have got a certain velocity, but the direction is changing, then we can say that it is accelerating. Now, we normally use acceleration to discuss the change in speed, the change in velocity, but it can refer to both. V is the end velocity, and U is the start velocity. In the alphabet, A, B, C, D, F, G, H, I, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. V comes after U, so this is the first velocity, this is the second velocity. Just a way to remember it. Acceleration is a vector, the direction is important. When a moving object has a negative acceleration, it can either be slowing down, called deceleration, or it could be increasing speed in the opposite direction. If a car is moving along a straight motorway at 70 miles per hour, then it has a negative acceleration, the car will slow down. But on the other hand, if the positive direction is chosen to be upwards, then a ball that is dropped will have a negative acceleration. So if I have a ball, if we're saying that this is upwards, and if I have a ball and if it's dropped, it will accelerate at minus 10 meters per second squared. It will be accelerating in the opposite direction as up. It's arbitrary. Here's an example of a question. And another. This equation you will find at the back of your exam guide. So it's not one that you have to memorize. And X stands for displacement. Now, velocity time graphs are slightly different to distance time graphs. Distance time graphs, obviously, have got distance on the y-axis, usually measured in meters. But this is a velocity time graph. It gives more information than a distance time graph. It gives you speed, distance traveled, time. You can also figure out the acceleration. Although the line shapes look the same, the axes are different, meaning the line meanings are different too. So if we have a line that is increasing, so t equals 0, my line is sloping up, the gradient is at a certain amount, I can figure out the acceleration of that object. It went from 0 meters per second to 20 meters per second in 20 seconds. How did I do that? I did my intercepts. So this line finishes there, 20 seconds and 20 meters. So if acceleration is delta v divided by t, change in velocity divided by time, the difference between 20 and 0 is 20 divided by the time taken, 20. Acceleration was 1 meter per second squared. This object was increasing velocity by 1 meter every 1 second. Where a distance time graph said that this line was stationary, in a velocity time graph, it means that the object is traveling at a steady speed. Between the time of 20 seconds and 40 seconds, this object was traveling 20 meters per second, and that didn't change. You can also get the distance traveled. So two things you can get. You can get velocity from reading the axis on the graph. So at 5 seconds, what was the velocity of this object? Well, at 5 seconds, the velocity of this object was 11 meters per second. Draw my intercept. You can get the acceleration by finding the gradient. Now, the gradient means the difference in y divided by the difference in x, but that is the exact same thing as saying delta v divided by time taken, which we just did in the past page. The distance traveled is the area under the line. To find the area under the line, you just need to draw out the shape of the shape that is under the line. So for section A, what was the total distance traveled? Well, I have to find the area of that triangle. And to find the area of the triangle, it's 1/2 times height times base. So it'll be 1/2 times 20 times 10, 20 times whatever that number that is. I don't want to do maths in here in case I get it wrong and then people will laugh at me. I can find the distance traveled for section B as well. I just have to find the area of this rectangular looking thing. Now, the difference between 10 and 5 and 15 and 10 is 5. The difference between 20 and 0 is 20. So I do 20 times 5, and I know that that's 100. So the distance traveled was 100 meters. Try these ones. How do we investigate motion? There are going to be two videos put underneath this. There's going to be some videos, pardon me, put underneath this video on YouTube. They link you to the Pearson website, which will allow you to watch how to do these core practicals. So these core practicals will be coming up in your exam in some way, so you must watch the videos. If you would like to, you can arrange for myself or Mr. B or Miss C to go through them with you after school in lesson 6. We do have to remember some typical walking speeds, some typical speeds, some typical speeds of everyday objects. The wind is variable from 5 to 20 meters per second. Walking is 1.5. You can double that if you run, and you can double that if you cycle. And cars in towns go about 13 meters per second, while cars on motorways can go 31. The speed of sound in air is 330 meters per second. And just for the sake of it, the speed of light is about 300 million meters per second. Also written as c. When a skydiver jumps out of a plane, they may reach terminal velocity. At terminal velocity, the pull of gravity on the skydiver, pulling you down, say it's 500 newtons, it's a small skydiver, but there you go, is equal in size and opposite in direction to the air resistance on the skydiver. As there is no resultant force, there is no acceleration, and the skydiver will fall at a steady speed. Fun fact, if you drop a squirrel onto planet Earth from outer space, it will die of starvation. It will not die of hitting the ground. Squirrels can survive their terminal velocity. Woo! The acceleration in free fall is 10 meters per second squared. So every 1 second that you're falling through the sky, you will be increasing your velocity by 10 meters per second. The weight will not change, but will have a constant downward pull. You will have a constant downward pull by gravity. Air resistance and drag will be pulling the skydiver. Will be having an opposite force upon the motion of the skydiver, and eventually it will go. The acceleration will go to 0 meters per second squared. So this is where we just jumped out of the plane. Ugh. And for a little while, the weight is going to be greater than the air resistance that is acting upon the skydivers. So at this point, there will be acceleration. Eventually, though, the acceleration, the force downwards will balance out with the force upwards, and there will be 0 acceleration. At that point, they will be falling with terminal velocity. Terminal just means the end. You cannot go any faster unless you're being pushed by something. Here are some estimations of everyday accelerations. And some questions. And the answers? Okay, so a typical person's reaction time varies from 0.2 to 0.9 seconds. Generally, the older you get, the slower your reactions. The younger you are, the quicker your reactions. If you're into sports, you'll have faster reactions than somebody who's not. And if you're a PlayStationer or an Xboxing person, then you will also have very fast reactions. There are a number of factors that will affect your reaction time and in turn thinking distance. Now, thinking distance is if you are driving along and suddenly you see a hazard, something in the distance that might hurt you. You think, oh, look at that. At this point, you see the hazard and you start to react. Your brain, you send a message to your brain sends a message to your foot, and all that is taking time. Meanwhile, your car is still carrying on. If you were going at 10 meters per second here, you're going to continue going 10 meters per second at this point. Your car has not slowed down, but it takes a bit of time for your body to react. As soon as you start pressing the brake, your velocity will decrease. So it will become less than 10 meters. It will become smaller than 10 meters per second, say 9 meters per second or whatever. The distance that you travel while you're thinking about stopping is known as the thinking distance. So if you slow your reaction time, then if you increase your reaction time, if you slow your reaction speed, then your thinking distance will change as well. Alcohol increases your reaction time. It makes your thinking distance bigger. Caffeine decreases your reaction time. It makes your thinking distance smaller. Tiredness increases your reaction time. It makes your thinking distance bigger. Distractions increase your reaction time and makes your thinking distance bigger. Drugs can either increase or decrease reaction time. As some drugs are stimulants, this is going to decrease reaction time. And some are depressants. This is going to increase reaction time. Now, do all stimulants make it so that it's safe to drive? Absolutely not. Because if you have an overly increased reaction time, if you're overly stimulated, then distractions are going to make you a very poor driver. A person's reaction time is very short. To measure the reaction time, you can either do online tests that display a stimulus and measure the time taken to respond to the stimulus, often by clicking a mouse button or a spacebar. The ruler drop experiment is where we drop a ruler through your hand. As soon as you see the ruler move, you close your hand. The distance the ruler moves through your hand corresponds to a given reaction time. You can find those two at the reaction at the website that was just down there. I have some definitions. Thinking distance is the distance that you travel while reacting to a stimulus until you get your foot onto the brake. Thinking distance depends on reaction time, but these are not the same thing. Braking distance, why are they not the same thing? Because, you can have a very fast reaction time, but you could be very stupid. Or you could be very quick, very, very clever with a very slow reaction time. You could have seen it and dropped your phone while texting or whatever, and that's going to impact the whole thinking distance as well. Braking distance is the distance you travel from pressing the brake pedal until you come to the stop. Now, there's going to be loads of things that affect braking distance as well. Stopping distance then is the sum of thinking distance plus braking distance, and it is shown as the equation below. Stopping distance equals the distance it takes for you to think about stopping, and the time it takes for your car to stop, the distance it takes for your car to stop. One of the biggest things that can affect the stopping distance is the speed of the vehicle. Highway code picture that you see here shows the stopping distance for cars at various speeds. So even if you're just going 30 miles per hour, it can take up to 23 meters to stop. So even if the bigger the speed, the bigger the stopping distance. When you double your speed, your thinking distance will also double. Your reaction time doesn't change, but you're going at twice the speed. Just have a read of this. So hopefully you've read this. If not, then just press pause, and then I'm going to say something. So while doubling your speed will double your thinking distance, your reaction time doesn't change. If you double your reaction time, then you will double the thinking distance. However, your braking distance will quadruple when you double the speed. And the reason for that is it's velocity squared. It's not just velocity, velocity squared. Because there's 4 times the amount of kinetic energy if you double your speed, it takes 4 times longer to stop with a given braking force. Here are some factors which affect braking distance. It's always important to bear in mind this idea of friction. They love talking about friction in their exams, so just make sure you understand that. Have a pause. Now, braking force. When a force is applied to the brakes of a vehicle, work done by the frictional forces between the brake pads and the brake disc reduces the kinetic energy of the vehicle, and the temperature of the brakes increases. So we have got kinetic energy in the vehicle. It is going to be transferred by friction to a thermal store in the pads. The greater the speed of the vehicle, the greater the braking force needed. The greater the braking force required, the greater the deceleration of the vehicle. Large decelerations may lead to brakes overheating and or loss of control. And here are some questions. And your answers? Thank you very much for watching. See you all next time. No, wrong button. Okay, see you all next time. Oh, still the wrong button. Next time.